Assalamualaikum and hi everyone. Our group will be presenting our research on the relationship between inflation rates and gold prices in Malaysia. Gold is often seen as a safe haven during inflation because its value tends to rise when currency weak. In Malaysia, where economic stability depends on domestic fiscal policy, currency changes, and global markets, this connection becomes even more complex. Our goal is to analyze this relationship using three types of models, which are linear, quadratic, and cubic. By comparing their accuracy and error patterns, we aim to find which model best explains the trend. This study can help us understand how gold prices respond to inflation in Malaysia and assist in better planning for investment, forecasting, and monetary decisions.
Now, I will explain how we apply the linear model using the least square method to fit a straight line of the form y equal to a plus bx. First, we begin by forming the matrix representation of the system. We use two matrices. Matrix A is x values, vector B is y values. And then we use to solve the system ax equal to b in a least square sense. And then we apply the normal equation A transpose ax equal to A transpose b. Solving this system gives us the least square solution, which is the best fit line y equal to 180.4643 plus 0.7654x. And then we calculate the error vector E equal to b minus ax. Last but not least, from the error vector, we compute the error magnitude, which is error magnitude equal to 219.62. So, this is our graph of best fit curve against observed data for linear model. This graph shows the relationship between inflation in x-axis and gold price in y-axis. The blue line is our best fit linear model and the red dots represent the actual data points. As we can see, the line has a slightly positive slope, meaning that when inflation is increased and the gold price also increase. However, the actual data points are scattered far from the line, and this shows that the linear model does not fit the data well. There is no strong linear trend. Instead, the variation in data suggests a more complex relationship. Next, we move to the error vectors against x values graph for the linear model. This graph shows how the residual or error behave. Ideally, residual should be scattered randomly, but here we see a diagonal straight line pattern, which means the error follows a systematic structure. This pattern violates the key assumption of linear regression. The presence of a clear pattern tells us that the linear model is biased and unable to capture the complexity of the data. Hence, it proves that a linear model is not suitable and more flexible model like a quadratic or higher degree polynomial may be needed.
Here, we work on fitting a quadratic model of the form y equal to a plus bx plus cx squared to the given data using the least squares method. First, we represented the system in matrix form and computed the matrices A transpose A and A transpose B. Then we solved the normal equations to find the best fit parameters. The resulting quadratic equation we obtained is y equal to 185.01 minus 28.28x and 9.69x squared. Next, we calculated the error vector, which shows how much each predicted value deviates from the actual data points. Finally, we found the overall error magnitude, which is about 205.45, indicating the total deviation across all data points. This completes the quadratic fitting and error analysis for our dataset. Next, I will explain about quadratic fit between inflation rate and gold prices. This graph shows the result of fitting a quadratic regression model to the observed data of inflation rate and gold prices. Unlike the linear model, this curve reflects a non-linear relationship, meaning that the influence of inflation on gold prices is not constant. As we can see, the curve takes a U-shape. This indicates that gold prices are higher when inflation is very low or very high, but lower when inflation is at moderate levels. In other words, extreme inflation, either too little or too much, seems to push gold prices up. Visually, many data points are closer to the blue quadratic curve, suggesting a better fit than the linear model. This implies that the quadratic model is more effective in capturing the real-world behavior of gold prices in response to inflation. This model provides a better flexibility and realism in describing the relationship and prove that nonlinear models can often be more suitable when modeling complex economy variables. Next, we move to residual plots error vector against x, which is inflation. This figure shows the residual plots for the quadratic model. Residuals are differences between observed values and the predicted values by our model. Compared to the linear model, the residuals here are more spread out and less patterned, which means the model captures more of the underlying relationship. However, it's important to note that the residuals are not perfectly balanced. On the left side, we see some very large positive error, and on the right side, there are some negative errors. These deviations suggest that even though the quadratic models improve the fit, it still doesn't explain all the variance in the data. The lack of symmetry in the residuals show that the model may be underfitting or overfitting in certain regions. So, while the quadratic model is a step forward, the residuals suggest that a more flexible model, such as like a cubic, might be necessary to truly capture the complex relationship between inflation and gold prices.
So now we are using a cubic model to fit the data. For cubic model, the equation is y equal to a plus bx plus cx squared plus dx cubed. We turn the data into a matrix form, so we can use the least square method to find the best value for a, b, c, and d. Using this method, we solve the equation. This is the best fit cubic curve for the data. Next, we calculate the error. Will tell us how close our curve is to the actual data. So we use the formula error equal to b minus ax. Then we find the error magnitude, which means how big the total error is. And we'll get the result, 191.47. This number shows that how accurate the model is. If it's small, the curve is a good fit. But if it's a big, the curve doesn't fit well. So we can see from here is a cubic regression model fitting the relationship between inflation and gold price. So the red dots represent the actual data points. These are the observed gold prices at different inflation rates. The blue curve is the cubic model fitted to the data. Now notice the shape of the curve is not straight and it doesn't just curve once. Instead, it curves down, then up and slightly down again. So this means the model is capturing a non-linear relationship. From this picture, we can interpret that when inflation is low, around 0 to 1, gold prices decrease slightly. When the inflation increase, around 1 to 3, gold prices start rising again. But beyond that, around inflation 3 to 4, the increase slow or reverse slightly. So this tells us that gold prices don't respond to inflation in a simple or consistent way. There are psychological and market forces involved, such as investor confidence, demand for gold during uncertainty, and speculation. The cubic model, which allows for two turning points, minimum and maximum, is able to capture this complexity, something a linear or quadratic model cannot do. So overall, this model better reflects how gold price behave across different inflation levels. Okay, now moving to the next slide, which is this is the residual plot. It shows how well the model fits by displaying the error or difference between actual and predicted values. Here, each red dots represent an error value at a particular inflation level in x-axis. The vertical axis shows the size and direction of the error, whether the prediction was too high or too low. What we want to see is no clear pattern, and that's exactly what this figure shows. The residuals are randomly scattered around the zero line. There's no visible trend, grouping, or curve. The spread of errors is relatively small and balanced on both sides. So from this, we can see the model does not systematically overestimate or underestimate the gold prices at any point. The model has successfully captured the true underlying pattern in the data. In short, this kind of residual pattern is a strong indicator that the cubic or higher degree model is a very good fit for this dataset. Compared to simpler models, this one gives more reliable predictions and better reflects the complexity of real-world economic behavior.
From our analysis, we tested three models, linear, quadratic, and cubic model, to find the best fit for describing the relationship between inflation rate and gold price. Based on the error magnitudes, the cubic model produced the lowest error at around 191.47 compared to higher errors for linear and quadratic models. This means the cubic model captures the pattern in our data more accurately, likely because the relationship between inflation and gold price isn't simply straight or slightly curved, that may involve more complex fluctuations that the cubic equations can accommodate. By selecting the cubic best fit curve, we are better able to model how gold prices respond to changes in inflation, which is crucial for understanding trends, making predictions, and supporting decisions in financial planning or investment. In conclusion, choosing the cubic model aligns perfectly with our project objective, as it provides the more precise representation of how inflation impacts gold prices.